Good day, students. Today we are going to discuss about NP hard and NP complete problems, which is in your fifth unit. Okay. See, we have to know what is the need for learning this NP hard and NP complete algorithms. We learned in DA till now, we have learned what are the different types of algorithms which has different time complexity. Basically, if we categorize, we have two types. One is polynomial time algorithms and another one is exponential time algorithms. We always search for an algorithm which has lesser time complexity. So what is our ultimate aim is to reduce the time complexity by writing better algorithms. And ultimately, we have to reach a better algorithm every time. That is the new improvement. And this topic, this NP hard and complete, provides the guidelines for developing such better algorithms in future. And our ultimate aim is to develop a constant time algorithm which is so quick and it's the most efficient algorithm, which is an ideal case. From the previous case, we got to know there are two categories of algorithms. One is polynomial and exponential algorithms. If you refresh your previous units, we'll get to know like what comes under polynomial algorithms and what comes under exponential algorithms. And if you refresh it, linear search has n as a time complexity, binary search has log n, and insertion sort has n square, and merge sort has n log n. And when you look for exponential algorithms, which is of time complexity 2 power n, we have problems like 0 bar n knapsack problem, traveling salesman problem, sum of subsets problem, Hamiltonian problem, graph coloring, and so on, and much more, which has time complexity of 2 power n. So what is the inference from this time complexity is obviously our exponential algorithms are much more time consuming when compared to our polynomial algorithms. And as I told in the previous slide, the framework for converting our exponential algorithms to polynomial algorithms is called as NP hard and NP complete problems. And we'll see each and everything in detail in further slides. So in this slide, we'll see how to convert our exponential algorithms to polynomial algorithms, and this can be done in two ways. One is by by writing deterministic and non-deterministic polynomial algorithms for existing exponential algorithms, and another way is by finding a base case, that is a problem which can act as a base problem, which is similar to all other exponential problems, can be taken up, and we can find polynomial algorithm for that base problem so that it addresses all other exponential problems. Likewise, we can do. So in the first way, as I told, we can write deterministic and non-deterministic polynomial algorithms. So you have to know what is meant by deterministic and non-deterministic. So deterministic means we know what will be the output of this program and how much time it runs exactly. If it is a non-deterministic algorithm, we have certain methods or procedures that will, which we will expect it to run in, we assume it to run in polynomial time, but we actually don't know what will be the implementation for it to run in polynomial time. We just give a list of methods that has to be that has to work in polynomial time. That's what is non-deterministic. It means that we'll have random solution for every run of the program. Okay, as per, like, for example, if you have 0 bar on abstract problem, you'll have you can take first item, second item, and third item. That itself might give you a maximum profit. Always first item and third item only will give you the maximum profit. Likewise, we'll not know at what is the best solution. Random guess we make, and we try all possible cases, right? So that's what is non-deterministic. We don't know what will be the solution for each and every input of your program. So with random solution only, for it has random solution for every run of the program. Okay. So likewise, if you are writing a sample code which has certain procedures, and we assume that procedures to run in polynomial time without knowing the actual implementation of it, that is called as non-deterministic algorithm. And in successive slides, we'll see the example for how to write a non-deterministic algorithm. Okay. So in this slide, we'll see an example for non-deterministic algorithm. And what is the purpose for writing a non-deterministic algorithm is giving a gist of procedures, giving a list of methods for a problem statement, assuming that these methods in future will be turned from an exponential time algorithm to a polynomial time algorithm. That is, we are leaving these methods in the hands of future researchers for them to write a routine or procedure for turning these methods from exponential to polynomial time algorithms. So non-deterministic algorithms basically assumes certain methods to be written in polynomial time algorithms. For example, if you see here, it is a search search problem state. The problem statement is searching an element from an array of elements, and it will return true if an element is found, and it will return false if an element is not found. Okay, that is choice is a method which chooses a value from the array element, and success is a method which returns one or success if a solution is found, and failure is a method which returns that the solution is not found, that is the element is not found. Okay, so here in this procedure we have three methods: choice, success, and failure, and we are assuming all these three methods are working in O of one time, that is in polynomial time. But we will not know how this method works in polynomial time. We have given an assumption, and we have just written a non-deterministic algorithm stating that these methods has to be explored in future for them to be converted to a polynomial time algorithm. So it is left in the hands of future researchers for them to explore these methods and write procedure for these methods which has to work in polynomial time. Okay, that is the purpose of writing this non-deterministic algorithm. So basically it gives us a list of methods which has to be explored and which has a exponential time algorithm that has to be converted into a polynomial time algorithm. Okay, that's why we have a heading as magic into procedure and future. So all these choice, success, failure, everything is a magic method which doesn't know how its procedure is written. We assume that its running time is polynomial time, that is O of 1, and it is left to the future researchers so that they can explore and they can discover a procedure or routine for this method to run in polynomial time. In this slide, we'll see what is NP&P, which states the polynomial and non-polynomial problem-based algorithms. And see, if you, as from the previous slide, we told what is the importance of writing a non-deterministic algorithm. And one such explored non-deterministic algorithm was merge sort. For example, previously merge sort was in the category of non-deterministic polynomial algorithms. They have written a procedure for merge sort, which was a abstract procedure which was assumed to be running in polynomial time, but which was not actually running in polynomial time. And merge sort was explored by the researchers, and it was changed from non-deterministic algorithm to deterministic algorithm. That is, deterministic algorithm means we know the procedure which runs in polynomial time, and we know the details of that procedure as well. Okay, can you understand? So basically, as I told, we can convert our exponential algorithms to polynomial algorithms by two ways. One is by writing your non-deterministic and deterministic algorithms. So the need for writing a non-deterministic algorithms is non-deterministic algorithms gives abstract details of your methods, which is assumed to be running in polynomial time algorithm. And if any researcher has explored, and if he has given the procedure, and if he has given the details of that procedure which runs actually in polynomial time algorithm, then it is assumed to be a deterministic algorithm. Like that, in this example we have merge sort, which was previously a non-deterministic algorithm and which has been currently converted into a deterministic algorithm of n log n time, okay, which is a polynomial time. So in this slide, we'll see what is the next way in order to convert your exponential algorithms to a polynomial based algorithm. So what is the second strategy is to find a similar kind of problem which is similar to your exponential based algorithms. So one such problem is satisfiability problem. So what is satisfiability problem is, we have, for example, I've taken three variables over here. One is x, y, and z, and for each and every time each variable can take a binary input, either 0 or 1. So we'll not know what kind of what will be the input, right? So x may take 0 at one time and 1 at other time. Y may take 0 at one time and 1 at other time. Similarly z also. So possibly we'll have 2 power 3 inputs. Can you understand? For example, for first time we'll have 0 0 0, and for second time we may have 0 1 0, and third time we may have 0 1 1. It means x carries 0, y carries 1, and z carries 1. Likewise, our input may range from 000 to 111. Understood? Probably uh, 2 power 3 inputs, right? So we have to try all 8 values for our 3 variables, that is x, y, z, which has 2 power 3 possible inputs. So if you analyze this, this is similar to our exponential algorithm problem statements, right? For example, if you consider a 0 bar 1 knapsack problem, if we have three items that has to be included, I can include the first item or I can leave it. I can include the second item or I can leave it. Likewise, if you have n number of items, you can have n possible cases whether to include or leave it, right? So every time we have 2 power n possible set of inputs, right? So this satisfiability problem is also similar to that. Here I have 3 variables, so I have 2 power 3, and if it is a n variable, it will also be having a possible input set of 2 power n, which is similar to your exponential problem. So what is the idea of taking the satisfiability problem is, I have taken this satisfiability problem as a base case for all my exponential problems. So if I am able to solve this satisfiability problem, it means that I can also solve my other exponential problems. So I've taken a problem which is similar to my exponential problem, and if I'm able to solve this base problem, it also proves that you can solve all other exponential problems. For you to understand better, I have also given the state space tree. If you see that state space tree, so first node, it tells about whether to include my first value of x, that is whether what value to include in my first value of x, that is either it can take 1 or 0, and similarly y also can take 1 or 0, and z also can take 1 or 0. So if you go across the depth, for the first level, if you see, it takes the value x is equal to 1, y is equal to 1, and z is equal to 1. And in the second leaf represents x is equal to 1, y is equal to 1, and z is equal to 0, right? And similarly, you can understand the entire space tree, right? And this depicts the similar situation of our other exponential algorithms. That's why I have taken this satisfiability problem as my base case. So can you understand till now? So there are two methodologies for converting my polynomial exponential to polynomial algorithms. One is by writing a non-deterministic algorithm. Second one is by finding a base problem which is similar to all my other exponential based algorithms. And one such base problem is satisfiability problem. Okay. So from the previous slide, we understood what is a satisfiability problem and what is the need for taking satisfiability problem. Okay, and since satisfiability problem depicts a similar condition of all other exponential algorithms, it is satisfiability problem is also called as the NP-hard problems, non-deterministic polynomial hard problems, right? Because we do have a exponential time algorithms which is not converted into a polynomial time algorithm. So it is being told as NP-hard problem. Okay, and what is NP-hard reduction is, as I told in the previous slide, if you are able to convert your satisfiability problem into a 0 bar 1 knapsack problem, since it has some relationship among the exponential algorithms. So this concept is called reduction. That is, if I find a solution for my satisfiability problem, it means that I can also use that solution for my 0 bar 1 knapsack, graph coloring, traveling salesman, because all these problems are similar, right? So if I'm able to convert my solution of my satisfiability problem into a 0 bar 1 knapsack problem, that is called as reduction. That concept is called reduction. Can you understand? Can you understand what is NP hard? NP hard is satisfiability problem. If I convert my satisfiability into my knapsack problem, it is called as reduction. Okay. So assuming that, so satisfiability is a NP hard. It means that 0 bar 1 knapsack problem is also an NP hard problem, right? If the reduction is in polynomial time. For example, if I want to convert satisfiability into 0 bar 1, and if the reduction time process takes exponential time algorithms, exponential time, it is a waste of time, right? Reduction also should happen in polynomial time. If I'm converting a code into a other code for a customized problem, that conversion should also should take place in polynomial time. If it's happening in exponential time, then there is no use. That is the point of my third, that is the concept of my third point in the PPT. Okay, And it is also told that if I have a satisfiability problem solution which can be reduced to a problem L1, L1 is also a NP-hard, which you can understand from your second point, right? Satisfiability 20 bar 1 APSOC. And the fourth last point of the PPT tells that here the transitivity property also holds true. That is, if I have a solution for my satisfiability problem, which is converted to a L1, that is problem L1, and if L1 is converted to L2, it means that it is L it means that satisfiability can be directly converted to L2 as well, right? So that's how the transitivity property holds good in this NP-hard detection. Okay. So till now we have seen what is NP-hard, and in this slide we'll see what is NP-complete. So if a is satisfiability problem is a itself is a NP-hard problem, and if it is getting converted to another exponential based problem, and if that exponential based problem, consider here L is an exponential based problem, if that exponential based problem L has a non-deterministic algorithm means, then it is called as NP complete problem. Okay. Example, I have a satisfiability problem which can be converted to a 0 bar 1 knapsack problem. And for 0 bar 1 knapsack problem, if I am writing a non-deterministic algorithm, then 0 bar 1 knapsack problem with non-deterministic algorithm is called as NP complete problem. Okay, and I've also given a Venn diagram explaining the relationship between your NPP and complete and NP hard. Okay, so what is the idea in this Venn diagram is, your if you see the left side of the circle, your polynomial algorithms are a subset of your NP, that is your non-polynomial algorithms, obviously, right? So polynomial algorithms has linear time, that is your linearly increasing algorithm, time complexity algorithms are a subset of your non-polynomial algorithms, right? And if you want to understand this better, consider the example of merge sort, right? So merge sort, as I told before, it was a exponential based algorithm before. It was not a polynomial time algorithm before. So it was previously under the category of NP hard. Initially, it was under the category of NP hard, that is an exponential time based algorithm. And then it has got a deterministic, non-deterministic algorithm. And at the point when it has a non-deterministic algorithm, it became a NP complete problem. Understood? And when it becomes an NP complete problem, the researchers has explored and has written a procedure for it to become a polynomial problem. Understood? So now merge sort from non-polynomial problem, it has come to a polynomial problem. So now polynomial problem, so if you understand, all your polynomial problems are subset of non-polynomial problems. Understood? So all those where non-polynomial are getting converted into polynomial with the help of this guidelines called NP hard and NP complete. Can you understand? That is the relationship in this diagram. Understood? So if you consider for satisfiability, another example, if you consider satisfiability is, as of now, it is a NP hard problem. And if I'm writing a non-deterministic algorithm for satisfiability problem, it will become an NP complete problem, which is left to the researchers. And if any of you or any of the researchers are writing code for those generic methods or abstract methods, or methods for which the routine is not yet discovered, if you are writing a code that is running in polynomial time, it will be converted from NP complete to a polynomial time problem. Can you understand? So this is the logic behind this Venn diagram. So in this slide, we'll see about Cook's theorem. So what this Cook's theorem states, that is, any non-polynomial problem can be converted to a polynomial problem, right? That's what we have been seeing in previous slides. So this is the theorem stated, and it is a concept stating that it can be converted. Any non-polynomial problem can be converted to a polynomial problem, okay? And for example, as I told in the previous slide, satisfiability problem is a base problem for all our exponential based algorithms or exponential based problems, right? So if you are right, if you are able to get a solution for your satisfiability problem, it means that all my non-polynomial problems have been converted to polynomial problems. That's why I have written in my third point in the slide, I have written P is equal to NP. It means that all my non-polynomial problems can be converted to a polynomial problem. It means that everything has become deterministic. From non-deterministic, everything has become deterministic. So if this can happen, that's what this theorem states. Okay. So hope all our non-deterministic algorithms will turn into polynomial deterministic algorithms by future researchers. Okay. That's the meaning of this P is equal to NP. Right. So in the last slide, we are going to provide summary for all the previous topics which we have discussed. So basically, we know in DAA we have two types of algorithms, that is polynomial algorithms and exponential time-based algorithms. And this NP-hard and NP-complete provides a guideline or framework for working on all exponential algorithms that can be converted to a polynomial time algorithm. Okay, and an example is this can be done in two ways. Either you can straight away take an exponential problem, write an non-deterministic algorithm for that problem, make it as NP complete, and leave it to the researchers to find the procedure which runs in polynomial time. So that if you find the procedure which runs in polynomial time, it will get into your P. That is your P kind of problem. That is your polynomial kind of problem. This is one way. And another way is finding a problem, a base problem, which is similar to all your other exponential problem, stating it as NP hard, and then writing a non-deterministic algorithm for that NP hard problem. And that NP hard problem, after writing non-deterministic algorithm, it becomes NP complete and leaving it to the researchers for them to explore and discover the method procedures which runs in polynomial time and ending up in polynomial time algorithm. So this is the flow: NP, NP hard, NP complete, and polynomial. Okay, this is the flow of it. And Cook's theorem, what it states is we can convert a non-polynomial algorithm to a polynomial algorithm with the help of this guidelines NP hard and NP complete. Understood? That's what is the concept in this topic. Hope you can understand, and hope you can understand this better. Thank you. Thank you guys for listening. If you have any doubts, you can drop your questions in your respective WhatsApp class groups or to your faculty. Okay, stay safe at home. Thank you.